one more example of electrophilic aromatic substitution. In the previous video, we looked at Friedel-Crafts Acylation. Now we're going to talk about Friedel-Crafts Acylation. In both Friedel-Crafts Acylation and Acylation, we're making a new carbon-carbon bond. In the case of alkylation, we're just adding an alkyl group. In the case of acylation, we're making a ketone right off the benzene ring. Just like the Friedel-Crafts Acylation, we're going to use aluminum chloride as a Lewis acid catalyst. Let's take a look at what our electrophile actually looks like. The active electrophile in Friedel-Crafts Acylation is called the Acylium ion. Now, the formation of this ion is very similar to the formation of the carbocation from the Friedel-Crafts Acylation. We have the chlorine acting as a Lewis base. The aluminum chloride acts as a Lewis acid in accepting that pair. We get this complex, and then the AlCl4 pops off as a leaving group, leaving us with the Acylium ion. Now, there's a pretty big difference between this Acylium ion and the carbocation in the Friedel-Crafts Acylation. In this case, this ion is resonance stabilized, and in fact, this quote-unquote alternate resonance structure is probably the better of the two, because in this one, all of the atoms have a complete octet. In this case, the carbon with a carbocation does not have a complete octet, and so this is the greater resonance contributor. And also, as a result of this resonance stabilization, and this being the strongest resonance contributor, unlike the carbocation that we make in the Friedel-Crafts Acylation, this one won't rearrange. And so we don't have to worry about carbocation rearrangement and getting those mixtures of products, which can be very useful in synthesis. All right, when we look at the mechanism, I think you're going to see this is very similar to many of these other mechanisms that we've seen for these electrophilic aromatic substitution. We start off with a nucleophilic attack. That generates the sigma complex with these three resonance structures showing the movement of the carbocation around the ring. And then we finish it off with the exact same proton transfer step that we saw in the Friedel-Crafts Acylation and in the bromination and chlorination. And in a step that could be really important for synthesis, the ketone that we produce in the Friedel-Crafts Acylation can in fact be reduced in a process called Clemmensen Reduction. If we take this aryl ketone and react it with a mixture of zinc and mercury with hydrochloric acid, we can get rid of this ketone, leaving us with just the alkane. And the reason this is noteworthy, in the Friedel-Crafts Acylation, I couldn't add this group to the benzene, because if I tried to add an alkyl halide with the chlorine here, we'd get rearrangement to this secondary carbocation and it wouldn't work. If you remember, most primary alkyl halides won't work in the Friedel-Crafts Acylation, but I can do the Friedel-Crafts Acylation followed by the Clemmensen Reduction to get the product that I was interested in. Another problem that we had with Friedel-Crafts Acylation is that polyalkylation was a problem. It turns out, due to the different nature of an alkyl group versus a ketone, we don't see polyacylation in the Friedel-Crafts Acylation.